So David, before we geek out on Helion's fusion approach, can we start with some basics? I think some listeners might still be fuzzy on what exactly sets fusion apart from fission besides the obvious rhyming thing.
Totally fair. In a nutshell, fission is what powers most of today's nuclear plants. It's like splitting apart really heavy atoms, think uranium or plutonium, and releasing a ton of energy. Fusion, on the other hand, is the opposite. You're combining light atoms, like hydrogen, to make heavier ones. That's the same process that makes our sun shine.
Right, so fission is splitting, fusion is joining. I always find it wild that we've harnessed the power of heavy atoms falling apart, but we still struggle to bottle up the sun's magic trick. Is it really just about how tough it is to get those tiny hydrogen atoms to fuse?
Exactly. Fusion sounds simple, just smash hydrogen atoms together, but you need to heat them to over 100 million degrees Celsius. The challenge is, at those temperatures, everything wants to fly apart, so you have to hold that searing plasma together long enough for fusion to happen. That's why the whole fusion is always 30 years away joke exists.
The classic moving goalpost. Quick side note, do you have a preference on pronouncing fission? I heard it's like vision in the US and mission elsewhere.
I'm Team Vision, but honestly, once you've been around nuclear engineers long enough, you hear every version. But what's way more important than how you say it is understanding how big the difference is between the two. Fusion promises clean, virtually limitless energy, and without the long-lived radioactive waste or meltdown risk you get with fission. That's a huge deal.
That actually reminds me, let's dig into where these fuels come from. Fission's got uranium, plutonium, but fusion is all about hydrogen's isotopes, right?
You've got it. For fission, we dig up uranium from the ground, same for plutonium, though most of that's actually made from uranium in reactors. That fuel is rare, and processing it adds its own headaches. Fusion's fuel is way more abundant. We use deuterium, a heavy type of hydrogen, and it's literally in the water you drink.
Wait, so there's fusion fuel in my coffee right now? That's pretty wild. How much deuterium is actually out there?
A mind-boggling amount. There's enough deuterium in Earth's water to power humanity for millions, maybe even a billion years at today's energy use. And it's safe, non-toxic, everywhere. No wonder futurists get excited about fusion.
And if we eventually run out, we're probably off colonizing other planets by then, right?
Exactly. If we ever burn through all our hydrogen, we're doing some seriously advanced stuff, probably spreading human fusion reactors across the solar system. But for now, the abundance right here is more than enough to dream big.
Switching gears, E equals mc squared, always pops up in these conversations. But what does that really mean in fusion? And why are those insane temperatures necessary?
Great question. E equals mc squared is Einstein's big idea. Matter and energy are two sides of the same coin. In fusion, when you fuse two light nuclei, say deuterium, they form a heavier nucleus, but the new particle is a little lighter than the sum of its parts. That tiny missing mass gets released as a huge burst of energy.
So even a little mass lost gives you a ton of energy. But why does it take such extreme heat just to get these atoms to stick together?
It's all about overcoming the repulsion between positively charged nuclei. Imagine trying to force two magnets together the wrong way. They push back hard. At 100 million degrees, the hydrogen nuclei move so fast that a few slam together close enough for the strong nuclear force to take over and fuse them. Only then do you get that energy payoff.
Which is nuts, because all this is just particles racing around at unimaginable speeds. And, in fission, the uranium's already unstable, so you don't need nearly as much heat to get it going.
Exactly, uranium wants to split anyway. Just add a neutron and boom, chain reaction. Fusion's a much tougher club to get into. That's why we have to invent all these clever ways to confine and heat the plasma, since we can't just build a miniature sun with gravity like the real one.
Funny, you mentioned chain reactions and safety. Fusion always gets praised as meltdown-proof. But how does that compare to fission? And why can't fusion reactors be turned into bombs?
Here's the thing. Fusion is inherently safe because the process is so hard to sustain. If anything goes wrong, like a system failure or even something wild like a meteor strike, the reaction just stops. No meltdown, no runaway chain reaction. And crucially, fusion fuel itself can't be weaponized. You can't make a bomb just from deuterium and these techniques.
That's a big deal, especially considering geopolitics. Fission reactors can be engineered to be very safe, but the real risks are more about how people manage fuel and enrichment, right?
Absolutely. Modern fission plants are engineered well, but accidents like Chernobyl or Fukushima often stemmed from human decisions and operating old designs past their prime. Plus, uranium and plutonium can be used in weapons if handled badly. Fusion avoids that whole issue.
I love your analogy of only having a second's worth of fusion fuel in the system at a time. If you stop feeding it, it just shuts down. There's also way less radioactive waste, right?
Right. Fusion creates some neutron-activated materials, but nothing like the long-lived waste from fission plants. And with smart design, even that's minimized. It's a fundamentally different safety and environmental profile.
Let's get to the fun engineering stuff. The classic image is the giant donut-shaped tokamak, but helium is taking a different path. What's the deal with your magneto-inertial fusion and these field-reversed configurations?
Yeah, so most traditional fusion goes with either magnetic confinement like tokamaks or stellarators or inertial confinement like big lasers squashing fuel pellets. At Helion, we're blending both. We use pulsed magnetic fields to rapidly compress plasma in a straight line, not a donut, and create a self-organizing plasma structure called a field-reversed configuration, or FRC.
A self-organizing plasma almost sounds sci-fi. How does it actually stay together long enough for fusion? Isn't it kind of like trying to keep a spinning top from falling over?
That's actually a great analogy. The FRC wants to tilt or fall apart, but if you spin it fast enough by heating it rapidly to those insane temperatures, it stays stable long enough for fusion to happen. We've learned to design these systems to keep that plasma top spinning upright for thousands of microseconds, using fast electrical pulses and clever control systems.
And you're pulling this off using modern electronics and fiber optics, right? Because this all happens way faster than any human could react.
Exactly. Everything is pre-programmed, think assembly language, Python, even a bit of Fortran for the old-school crowd. We use real-time diagnostics to monitor tens of thousands of electrical switches, all firing in sync to create, compress, and control the plasma. No human could handle those microsecond timescales, but computers and fiber optics can.
All right, let's talk outcomes. Traditional nuclear and even most fusion designs convert heat to steam, then to electricity, losing a ton in the process. What's Helion's vision for getting power out more efficiently?
I love this topic. The cool thing about magneto-inertial fusion, especially with high beta plasmas, is that the energy released is already in the form of moving charged particles. Instead of boiling water and spinning a turbine, our approach lets us convert that energy directly into electricity, potentially at 80% efficiency or more. That's a game changer, compared to the 35% you get from steam.
So, in a way, you're moving from the campfire analogy holding heat in place to something more like a piston engine, where the plasma's own pressure does useful work directly. That's pretty wild.
Right. The plasma compresses, fuses, then pushes back on the magnetic field, and we extract that energy as electrical current. It's like turning the explosion inside an engine straight into forward motion, but here, it's pure electricity. And because there's so little fuel in the machine at a time, you get all the safety and environmental perks too.
What's really exciting is that, if this works, fusion could unlock a new era of energy abundance and change pretty much everything about how we live, work, and even solve global challenges.
Absolutely. It's not just about clean electricity, it's about lifting the constraints on what's possible for humanity. Every leap forward agriculture, machines, the digital age came from unlocking new energy. Fusion could be the next giant leap, and we're closer than ever.